Hello students, in the last session we completed Newton 3 laws. We did see all those stuff that were related to Newton laws. Okay, so and then we have started like introduction to the friction, fine. So that's what we did see in the last session. In this session we will do rest all of the theory part that are related to friction. We will complete it. It's a kind of second half, right? Then we will do 4 different cases, okay, so that are related to fictitious forces. While doing that case, I'll tell you what is meant by fictitious force. As if now we will do like 4 different cases that are related to some fictitious force. It's a kind of equation balancing stuff, okay. So we will draw free body diagram and all those things in the next session, which means the final session for this theory part, where we'll be doing in the third session we'll be doing like leftover all other concepts, okay. There will be like car moving on a circular track, and then banked road, and then some extra concepts related to contact forces, fine. So these are the stuff that we will see in the laws of motion chapter, okay. So now we will start from the part where we have left in the last session, okay. So here you have got the friction that we were studying in the last class, okay. So here I have just drawn a diagram. So diagram is such that you have an object and then I'm going to push the object, okay. So in the situation, let's put it this way: you're having an object, I'm going to push it towards the right. Initially, this is something that I've explained in the last class itself, so you shouldn't have any doubt. So initially it will give you the opposing force, right? So when the opposing force isn't good enough to balance that force that I'm giving on this object, it will start moving, right? Once it crosses the F max, it will start moving. So before crossing the F max, I have told you there is something called static friction, okay. So static friction will be greater when compared to the kinetic friction, because the static friction is actually kind of a starting stuff, okay. You might have felt when you're going to push an object, initially it will be tough. Once the motion has begun, it will be easy for you to push the object, right? So from that understanding, I'm just going to tell you like 2 different things, which is like static friction and the kinetic friction. Got it? So static friction will obviously be greater when compared to the kinetic friction, because there will be interlocking, or else the molecular forces that is between 2 different surface might have been greater, okay. Because of that reason, initially it will be hard to push, then it will become easy, okay. Comparatively easy, not like little bit. The opposing frictional force will be less. That's what I'm telling you here, okay. So based on that notion, I'm just going to draw a diagram over here. So here on the x-axis, you have got the force given by me, which is the force that I'm giving to push this object, and the same way the frictional force, the opposing frictional force that is generating between the surface, is actually plotted along the y-axis, fine. So that is how the graph is. Then what actually I'm doing here is, when I give like 1 Newton force, the frictional force is good enough to balance, therefore the opposing force will be of 1 Newton, the object will be rest, which means at static position. Then when I give like 2 Newton, that even in that situation the frictional force was good enough to balance it. Then there came a peak point where the frictional force wasn't good enough to balance that one, so the object started moving. So that peak point is called the static friction, okay. So that friction is called as static friction. I'll notate it as like F subscript small s, okay. So that is how I'll notate that static friction. Then once the motion has begun, as I have told you, it will become easy for us to push it, which means the opposing frictional force has reduced by some degree, okay. So after the motion has begun, the frictional force will be less when compared to that of the static friction. So that less frictional force that is given on that particular object is called as static friction, kinetic friction, okay. So F subscript small k, okay. So that is how you'll have to understand this diagram, this graph, okay. So based on this understanding, so based on the experiment that I'm doing, it is obvious that the frictional force, opposing frictional force, actually depends on the mass of the object, okay. It doesn't depend on the shape or orientation, but it does depend on the mass. More the mass, it becomes harder for us to push, so it should depend on the mass. Instead of taking the mass straight away, let me do one more example to it. Let's put it this way: you have something called book on this table, and then I'm pushing it, okay. It will be easy for me to push, okay, in the first case. In the second situation, if I'm just going to give some extra force by placing my hand on it, and then if I want to push that book, it becomes harder because I'm just giving extra force into it. So even though the mass of the book was just the same in both those situations, in the first case I didn't give any external force. In the second case, I did give external force. When I gave external force, it became harder for me to push, which means the opposing friction was greater. So it seems to be pretty obvious. Friction does depend on the mass, not in the fashion that I expect. It actually depends on the mass in terms of normal force. Okay, so more the normal force that is acting on that object, you will have like greater friction, which means more you squeeze two objects together, then in that situation it becomes harder for us to push. Okay, therefore friction depends directly on the normal force that is acting on that particular object. Okay, so you should be clear with this thing that I'm telling you. Anyway, while doing those cases, different cases that I've told you, we'll come across this concept one more time, right? So F directly depends on the normal reaction. Normal reaction is actually the upward reaction that is being generated, okay, because of the mass and the external force that I'm giving on it, right? Okay, so then F is proportional to N, normal reaction. So it depends on the surface, right? It depends on the surface, it depends on the nature of the material. So it depends on multiple other parameters. It is not same for all those objects and then the surface thing, right? Therefore, F equals some constant times the normal force. Therefore, that constant is actually mu. It could be like mu k or mu s depending on the situation. So general formula that I could actually make from this one is mu n. Okay, so if this proportion F equals mu n, so in the question while doing PVQ, they'll just clearly give you whether it is mu s or mu k. If they haven't given anything that is related to static or kinetic, then you just substitute the mu straight away and do the solving sum. Okay, and do the solving for the sum, right? Fine. So this formula should be clear. Then what I did is I just wrote this one in two different formula representing static and then the kinetic stuff. So Fs, so frictional static, will be equal to mu s n. Okay, where mu s is coefficient of static friction. I've already explained to you. Then you have got like Fk, which is equal to mu k capital N, where mu k is nothing but the coefficient of kinetic friction, right? So these two are constant. So we'll be able to get this mu k depending on the surface that I have chosen in which I'm going to move the object. Same way, depending on the nature of that object also. Okay. So now what I need to find is I'll have to determine this mu s and mu k, right? So to determine this mu s and mu k, I'm just going to do a simple experiment. So you will get the answer straight away. Okay. So the experiment is also simple and basic stuff. What you've got over here is you have got an inclined plane and then I place the object. What I need to find here is the friction between this two surfaces. Okay, so one is the surface of that object and the other one is the surface itself in and itself. Okay, inclined surface. Got it? So then I'm just going to set it such a way that you start inclining this slopes a little. Okay, so you just start inclining this plane little by little and then there comes a point in time where it starts sliding. Okay, so that point where it starts sliding is called as theta max. So this angle is also called as angle of repose. Fine. So now what I will do is I'll just relate this angle theta max with that of the mu. Okay, so that's what I'm going to do, right? So to relate this theta max with the mu s, first what I need to do is I just have to resolve this mg into different components and then I'll have to put normal reaction and all those things, right? So when I do that stuff, I'll be able to balance the force along the x and then the same way the force along the y. Okay, so in that particular instant, fx and summation of force along the x and then the y will be 0. We'll do those stuff as if now I'm just going to split this mg and then the normal reaction that is acting on this particular object. Okay, so in the last class we did same free body diagram for this object on a flat surface. In this situation, I'm just doing it for the inclined surface. That's it. Okay, so I have got mg. I'm just going to resolve this one into two different components. Okay, so one will be like perpendicular to the surface, other one will be like parallel to the surface. So it will look something like this. So this will be perpendicular to the plane. So let's find what it should actually be, cosine theta or sine theta. Then another one component will be like parallel to the surface. Okay, so to resolve this component, I should know how does this theta relate with this angle. Okay, either it should relate with the bottom one or it should relate with the top one. Okay, so to relate these two things, so first let me give you an idea and perception. So you might have known from the previous classes. Okay, so I did use this concept to solve one of the sums. If you are clear with that sum, you should be able to understand this one straight away. Anyway, for the students who didn't understand that stuff properly, I'll just do it one more time. So this is just an easy one, okay? So this is how the angle is going to be, right? So this is the first angle, right? So you have got like theta over here. What I'm going to do is I'm just going to flip this angle by an angle of 90 degree. I'm just going to rotate this entire stuff by an angle of 90 degree. Then what will happen? So what will happen is this line will become perpendicular to this one because I've just rotated it by an angle of 90 degree, right? So that one will become perpendicular. Okay, so this line will become this way, and then this inclined line will cut the inclined line perpendicularly. Okay, so that line will be something like this, right? Obviously, right? So what I've done over here is I just rotated this first angle, the first one with an angle of 90 degree, and I got the second one. Then obviously these two angles has to be the same, right? So theta in both those situations has to be same. If this was theta, then actually this should also be theta. Okay, so the hint that I'm going to take from this understanding is the first line cut that line by an angle of 90 degree. Same way the other line cut the other line with an angle of 90 degree. If that was the case, then these two theta should be equal, right? Let us match that one in the situation. Here you have got this horizontal line, and the horizontal line is cut by mg perpendicularly. Yeah, and then this inclined plane is cut by this line perpendicularly. Then obviously this theta and this theta should be same, right? Simple, easy understanding. Therefore this angle will be like theta, right? Okay, so if it was the point where it starts sliding, I'll be able to put this one as like theta max. That's it, finished. Okay, so now I'll just put a theta and then I'll do the solving, then I'll change it to theta max. Fine. So this component that is close to theta will obviously be mg cosine theta, right? So this component is like mg cosine theta. Fine, so that is closer to theta, and the one that is apart from the angle will be like sine component, therefore it will be like mg sine theta, right? So now I have got both those components into it. Then let us put like normal reaction, obviously. So in the first situation, let me take it that in this fashion, that you haven't moved it to a point where it starts sliding. It is before that point. So in that situation, that object will be at rest, right? Even at the point where it starts sliding, the friction, everything will get balanced. Therefore, even in that situation, summation of f of x and y will be like 0. But the point that I'm insisting over to you over here is there isn't any motion. If that was the case, obviously the friction should be able to balance just all other stuff, right? So here for this mg cosine theta, there will be a normal reaction because this entire object will push the surface downwards by a force of mg cosine theta. Then the opposing force will be like the normal reaction. So that will be like capital N. Okay, so this will be my normal force. Got it? So this one wants to slide down by mg sine theta. This one wants to slide down with the force of mg sine theta, but obviously this isn't going to slide because you have like opposing friction acting on it. Therefore frictional force will be opposite to that of mg sine theta, right? Okay, so the opposing force will be like friction that will be balancing this mg sine theta, right? If it has reached f max, in that situation this will be like theta max. So that will be the point where it will start sliding. Okay, so that will be the point where it will start sliding, which means mg sine theta and f max will be same. Okay, so if mg sine theta completely balances the f max, that will be the maximum friction that could be generated between these two surfaces, right? So if that's the point, then this will start sliding, which means if I just give a small push to it, it will just move with a constant velocity. There wouldn't be any increment in the velocity, but the point is it will move with the same velocity. There wouldn't be any acceleration. Okay, so in that situation mg sin theta will completely balance f. Okay, if contact more than that, then both those forces on the left and the right will be like the same thing. If I just give a push, then that's the Newton first law, right? It will move with that constant velocity. That's what it's going to happen when I am going to put this theta to the maximum point, which is called as angle of repose. Okay, so you should be clear with all those things that I have discussed over here. Now I'm ready to do the force balance along the y and then the force balance along the x. Okay, so now I'm just ready to do it, which will be like summation of f of y, that will be like summation of f of y, that should be equal to 0. Okay, same way summation of f of x, that too should be like equal to 0, right? So now let me do the addition for the y direction. So here in this situation, this will be my y. So I took x and y axis with respect to the inclined plane. So this will be the vertical, because I'll be able to match the n with the mg cosine theta. Therefore, I took it this in this fashion. Same way, x will be like this one, horizontal to the inclined surface. Okay. So here, the first situation, n directly balances the mg cosine theta. Therefore, you will have n j cap, which is like acting upwards, and the same way you'll have mg cosine theta minus j cap, which is like acting downwards, exactly opposite to it. So that should be equal to 0. Okay. So these two things will be like equal to 0. And then if I just do the rearrangement thing, you'll have n normal force in this situation on an inclined plane will be equal to mg cosine theta. Okay, so it's not equal to mg, it's equal to mg cosine theta, because it is inclined, only some part of the mg is responsible for that normal reaction, right? You should be clear with this stuff. Then I'm just going to do the force balance along the x-axis. If I do it along the x-axis, you have got one component towards the right, which means towards the up, and the other one towards the down. Okay, so let me take the F to be like positive. So you'll have like F I cap frictional force, which is opposing the mg sine theta. So that will be like plus mg sine theta minus I cap. So this entire object isn't sliding down. Therefore, it should be f of x, summation of f of x should be equal to 0. Okay, so then I'll match it with the theta max. Okay, so this will be like equal to 0. So if I do the rearrangement thing, you'll have like f, which is equal to mg sine theta. Okay, so F will be equal to mg sine theta. So the frictional force that is getting generated directly depends on the mg sine theta. As I've told you, if like 2 Newton, if I just push it towards the right with the force of 2 Newton, then it could oppose with the force of 2 Newton frictional force, right? 4 could also be balanced. But if the upper limit was equal to 5, in that situation, both those things will get balanced, and then a slight push could make that object to move with that constant velocity, right? If force on the left and right are balanced, and then I couldn't go more than that 5 Newton. If that was the case, both those things are balanced, which means the net force on that object is like balanced. If I just give a push to it, what will happen to that object? It will start moving with the same velocity. If I just keep on pushing it greater than 5 Newton, then in that situation, the velocity will increase. You will have acceleration into it. Okay, but only thing is, I just balance the frictional force and then I just pushed it. So in that situation, it will move with the same force, okay, dragging along that surface, right? So that's how it's going to be. But in this situation, F, whatever the frictional force that is acting upwards, same way, mg sin theta was downwards, it was able to balance it. So that was the case over here. But the thing is, if the frictional force has to reach the maximum thing, which means F max was equal to mu s n, right? So that's how I did this one, right? Friction at the maximum friction was equal to mu n or mu s n, right? In this situation, as it was like static stuff, I'm just going to put it as mu s n. If it is like F max, in that situation, I'll just replace this F with mu s n. So that's the maximum friction that is possible to generate for that particular object in the surface. Okay, so it could a lesser force, frictional force could obviously be given. That's not a problem. So F will be like mu s capital N, which is equal to mg sine theta max. So now I just replaced with the angle of repose, which is called as theta max. Okay, so now it seems to be pretty obvious. Instead of n, I'll substitute like mg cosine theta and just cancel out mg cosine theta max. Okay, so that's the point where I was able to generate the maximum opposing frictional force, right? So instead of n, I'll substitute like mg cosine theta max into it. So you'll have like mu s mg cosine theta max, which is equal to mg sine theta max, right? Let me do that one. So you will have, so you are just going to have mu s mg cosine theta max, which will be equal to mg sine theta max, right? Now let me cancel these two things. mg will get cancelled out. If I just do the rearrangement, I'll get the mu s. Mu s will be equal to sine theta max divided by cosine theta max, which is nothing but tangent theta max. Okay, So that will give me the mu s. So mu s is the coefficient of static friction, right? So if you have to find mu s for a particular object with respect to that surface, what you will have to do is you just take that object, place it on a surface, and then start inclining it. There will come a point where that thing will start sliding. Okay, so that angle is called as angle of repose, right? So before that, the frictional force hasn't reached its maximum value, so that mg sine theta wasn't able to dominate for that particular object to move. When that particular point has reached, if you just give a slight push to it, it will start moving with a constant velocity v, right? So that particular point is the angle of repose or the theta max. Okay, so once you get the theta max, what you do is you just take tangent theta for that theta, you will end up getting the mu s, where mu s is the coefficient of static friction, right? So this is how we will be able to determine the mu for a particular object. Okay, so it should be clear. You should be clear with the theory part that I've discussed over here. Okay, you shouldn't have any confusion, right? There is this extra one statement which I've written over here, right? So this is something that we will see in the system of particles chapter. Okay, the logic and understanding behind it. So this is like in pure rolling condition, which means that rolling friction that I have discussed. Okay, so obviously rolling friction will be less when compared to static, and compared very much less when compared to static and then the kinetic friction. That's why we design wheel in circular shaped thing. Okay, so in pure rolling, if it was like pure rolling without any other external cause, for example, idealize the situation. Okay, so in that situation, no friction should actually act on the object. Okay, in that situation, frictional force acting on that roller or the circular shaped tire will be like zero. So that's what this statement represents. Okay, in pure rolling condition, no friction acts on the object, right? So we'll see the big intuitive thinking and all those things in couple of chapters ahead. As if now, only thing that you need to know is like there are like three frictions, which is like static, kinetic, and rolling. Okay, we have seen exhaustively related to static and then the kinetic friction. Rolling friction is something that I haven't touched. Only thing that you need to know is rolling friction is very less when compared to the static and kinetic friction, right? So we'll discuss all those concepts and understanding behind it in couple of chapters ahead, right? So now we have completed all the logic and theory that are related to friction. Now we are ready to jump into the last part of the session where we'll be doing like 4 cases. Okay, those cases are going to be exhaustive anyway. So where we'll be doing like 4 different cases with relation to fictitious force, right? So we'll see those things. Now we will see all those cases that are related to fictitious force, right? So we have like 4 different cases which we will see. Let's see the first case. Okay, so the first case is you got a truck that is moving towards the right with an acceleration a, which means you are going to freeze this truck at particular instant. In that particular instant, the velocity was increasing at a constant rate for the truck, which produced an acceleration of a. Okay, what I am interested in studying is actually the object that is inside the truck. Fine, so you got a load in that particular truck. I just need to study the nature of that load. How does the force act on that particular load? That's what I need to study. Okay, so I'm just going to draw free body diagram for this particular object. Free body diagram actually means you're just going to put all those forces that is acting on that object and just do the summation of forces along the y and then the x. Okay, so that's what we are going to do for this particular object, right? So now let me put all those forces. As you have mg that is acting downwards, obviously you will have normal reaction, because that is when this object will be at rest along the vertical direction, right? Obviously this is not going to break the truck, right? So you should have normal reaction that exactly balances this mg, which means forces along the y will be equal to 0, right? So you will have normal reaction. So this is the simple one. While doing normal reaction, I just did this one first, right? When you place an object on the flat surface, you will have normal reaction n, which will be equal to mg. Same thing here. So the normal reaction n is actually upwards, mg is downwards, right? So this thing is easy. Only thing that I'm really interested is along the x direction, fine. So if you just look at this object from the inside, what will happen? The entire truck is actually accelerating towards the right, which means this object will move backwards, right? Fine. So this is something that you might have experienced. If you just sit inside a car or a vehicle, whatever it is, when it starts dragging forward, which means when it starts accelerating forward, you will feel a backward force acting on you, right? This is something that we might have felt. Same thing is going to happen here. Okay, so that force is called as fictitious force. I'm just going to chain a guy here in the front. Okay, so he is chained, which means he's not able to move. when he looks at this object, the possibility is that it could actually fall backwards. Okay, if the acceleration is good enough, then in that situation it will fall backwards. That is possible. Or else if the friction is good enough to balance that one, then this will be a static condition. If the friction is not good enough, then it will start slowly progressively moving backwards. Okay, so that thing is also possible. Fine. So here I'm going to introduce a notion of fictitious force. Fictitious force actually means when you have an effect or force that is acting on that entire object externally, if you look at the object that is inside that particular environment, so it will have an opposing effect acting on this. Okay, so it will experience opposite effect to that of the effect that is entirely acting on that particular object. Okay, so if you consider the truck to be a single entity, the acceleration was towards the right. If you just only consider this mass, then this mass will move backwards with an acceleration, with the same acceleration but the opposite direction. Okay, so if you just have to imagine it in a different fashion, you could imagine it such a way. So initially the velocity of the truck was equal to 5 meter per second. Okay, so I'm just pressing the gas pedal, so 5 becomes 7 meter per second, so you with certain interval. Okay, so in that interval initially this object was also traveling along with the truck with a speed of 5 meter per second and everything was fine. Suddenly what happened is this entire truck became has raised its velocity to the final velocity of 7 meter per second. Okay, but the object that is inside this truck is still with the velocity of 5 meter per second. So what should happen to this object to match with this truck? It has to raise its velocity to 7 meter per second. That is when both those things will be in symmetrical motion and there wouldn't be any relative velocity between it, right? So to increase this velocity from 5 meter per second to 7 meter per second, so that this object is still inside this truck, what has to happen? Someone has to give force from the inside, so that will be the frictional force that is between these two surfaces. Okay, so if the frictional force was good enough, then without any movement of that object it will reach like 7 meter per second. Okay, if the frictional force wasn't good enough, if the surface was like slippery, then in that situation it will start dragging backwards. Okay, whatever acceleration that has produced forward, it isn't able to cope up with that acceleration, therefore it just moves a little bit backward, then it will gain its final velocity, which means it will just move a little bit backward. Okay, and then it will gain the final velocity. As I've already told you, you might have experienced that one inside a car, right? So same thing is happening here. But the point is, if the frictional force was good enough, then it will be able to balance in that particular position itself. Okay, if it is completely bad, if it is not good enough, then it will just fall backwards from that truck. Okay, that is possible, right? So the thing that you need to know is that if the entire acceleration was towards the right for this complete truck, then the object that is inside that truck will face the same effect in the opposite direction. Okay, so to cope up with this, so to cope up with that opposite effect, this thing has to give the frictional force, right? So here there are like two forces that is involving. One is obviously the frictional force. So as I told you, if you're just going to chain a guy in the front, then what you will see, he will just see this thing wants to move backwards, some for some arbitrary reason, but the thing is the entire stuff is accelerating forward. Okay, so when this thing wants to move backwards with an acceleration of a that is similar to that of the acceleration of truck. Okay, so if that was the case, then obviously friction will not allow, so frictional force will act opposite, which means towards the right in this case. Okay, so now I'm done with the force along the x-axis. Okay, so force along the x-axis will be like ma, which is towards the, I mean ma, which is towards the left. Okay, and then you will have friction that will act towards the right, obviously. So this will be the force along the x. If these two things balance each other, then in that case there wouldn't be any motion of this particular object. If the force was unbalanced, which means friction wasn't good enough to balance this ma, then with the rest force, which means if the maximum friction was like 5 newton, if the ma was equal to like 7 newton, with rest force it will start accelerating towards the left. Okay, so that's how it's going to be. So the net acceleration of this object is something that I should put on the left hand side, on the right hand side of this equation. Summation of force will be on the left hand side. If the net effect was like equal to 0, which means rest, then I'll put like 0 here, right? This is something that you should have known. Here in this situation, let me generalize it such a way that you have some acceleration into it. Okay, even after balancing some part of ma, you still have some ma left, therefore you are going to have an effect with which it is going to move towards the left. Okay, it should be clear. That is like, let us consider that acceleration to be like a dash. Okay, so that acceleration is like a dash after that subtraction. So summation of force along the x is not equal to 0 because the guy who is standing inside the truck is just looking at that particular object. It starts moving backwards, okay, with an acceleration of a dash, fine, even after getting balanced by the frictional force. So that will be equal to summation of f of x, which is equal to m a dash. This thing is done. Okay, now let me do the summation. So if I do the summation of forces, you will have F, which is acting along I cap direction, and then you will have plus MA, which is acting along minus I cap direction, which will be equal to MA dash. Okay, so this thing is done. So now instead of F, I'll have to substitute the frictional force. In this situation, obviously this started moving, which means F has reached its maximum. Still, it wasn't able to balance this mass. Okay, so instead of F, I'll substitute like mu k mg. Okay, as it is moving, it should be like the back kinetic friction. Therefore, I put mu k. So you will have mu k n. So n should be the normal. So normal will be equal to mg. Okay, that is pretty clear from the diagram itself. So for F, I'm just going to substitute mu k mg plus no. Let me remove those negative signs because it is only along the x-axis. Therefore, you'll have let me remove that I cap those stuff. Okay, so you'll have like minus ma, which is equal to ma dash. Okay, so now I can cancel out all those m's. M will get cancelled out. A dash is something that I need to find. So a dash will be equal to mu kg minus a. So a dash will be like equal to mu kg minus a. Fine. So you should be clear with this equation, right? So we will do sums that are related to fictitious forces. So this will be the foundation for those sums. Okay. So all those next cases that we are going to see in everything, this is the way that fictitious force is going to interact. The way it interacts is when you look at the system from inside, there will arbitrarily be an extra force that is getting generated. That is why it is called as fictitious force that got generated because you had some external effect to that entire system outside. Okay, so that is something that I didn't account. Therefore, when I look it from the inside, you'll have to put that extra force, which is called as fictitious force, opposite to that of the external effect. Okay, so that is what you need to know. So now I just found with what acceleration this is going to move backwards and fell from the truck, such that which will be equal to mu kg minus a, where a is the entire acceleration of that particular truck. Okay, so you should be clear with this first case, and then you should also be clear with the fictitious force that I've discussed over here, right? You shouldn't have any doubt. Then we will see the lift case. Okay, so the second one is based on the lift. Fine, so second case is based on the lift. You have a guy who is standing on the lift. Okay, when the lift is at rest, it is just the normal condition. It is same as that of a person who is standing on the earth. Okay, so that is something that is not fine. So now what happens is the lift starts accelerating upwards, which means it started moving upward from the ground floor. Okay, so when the lift starts accelerating upwards, so after certain instant, lift will move with the constant velocity. That is a different case. So that's a normal thing. So once the motor on the lift runs, what happens? The lift will start moving upwards. In that particular instant, the velocity of me is actually changing because I'm standing inside. Initially I was at rest, then suddenly I started gaining some velocity. Let me put it this way, I started gaining velocity towards the upward direction, and the final velocity was equal to 1 meter per second. So in that particular instant I was getting accelerated upwards. Okay, so that's the instant that I'm going to consider for the first case. So the lift started accelerating upwards, so acceleration was equal to a, and then after some time, it after like 2-3 seconds, it will reach a constant velocity. Okay, so that's a different thing. In that situation, I'm at a constant velocity, but in the instant where it started accelerating upwards, okay, when it started lifting me upwards, I'll feel that acceleration. So that acceleration is given over here. Okay, that's the external effect that is happening over here. Then what could be the internal thing that is happening? So internally, if I just don't consider this one, what will be the force that is acting on this object, mg, on this guy? Mg will be downwards, and then that is going to be a normal reaction. Okay, so that's the normal one when you don't have any external acceleration. But in this situation, you had an acceleration upwards. Then what should be the thing with that particular guy? You should have the same effect that is acting opposite for the one who is inside, right? So the acceleration that he is feeling from the inside will be like downwards. So that will be equal to A. Okay, so this will be the free body diagram for this particular guy. Okay, so N will be like upwards, same way mg will be like downwards, only acceleration will be like downwards. Instead I should generate force, therefore I'll multiply it with ma. So now I'm done with the free body diagram. Here the fictitious force is this ma that is getting generated because of this entire upward acceleration. Okay, so only thing that I'm interested is on this particular person, therefore I'll just have done the free body diagram for that person. Okay, now you don't have any component along the x, therefore I do not want to worry about that one. Only thing that I'm interested is about the y component, therefore nj cap and then mg plus ma minus j cap, right? Now let me do the force balance stuff, you'll get it, right? So before doing the force balance stuff, now I'll have to put the right hand side, right? Either it should be like ma dash as if here, or else it should be like 0. In this case, the person who is standing inside, if I put some object, some person over here, and then he is looking at this guy, he knows from inside this guy that is not moving, he is just stable, which means the net acceleration of this object from the outside is something different. For a person who is standing inside and looking at him, he is not feeling any motion, right? Therefore the force has to be 0. Summation of force along the way is 0. But in this case, that was something different. Okay, this object, for a guy who is looking at this object from inside, he also saw that this was accelerating backwards with some acceleration. Okay, so that was like a dash, it just fell back. But that's not the case here, right? Because of this normal reaction, he's not going to jump, or he's not going to get pushed up. That's not going to happen, right? So therefore, obviously, for a guy who is standing inside the lift and looking at him, he's not going to move. Therefore, summation of y forces along the way should be equal to 0. Okay, logic should be clear. Therefore, summation of forces along the way was equal to 0. Okay, so now let me do the free body stuff. Okay, equation balancing stuff, we'll get the answer. So if I do that one, you will have n that's acting upwards, so n j cap, and then you got like plus mg minus j cap, and then plus ma minus j cap, which was equal to 0. Okay, I think the arrangement is done. Now if I just do the rearrangement thing, I'll just get the answer. So n, which is equal to mg plus ma, because when it moves to the right hand side, those two negative terms becomes positive. So you will have mg plus ma. So what actually happened here is, I'm just going to feel some extra weight because you are having extra normal force acting on me. It is something like you're just carrying an extra backpack on your shoulder. Okay, so you will have to balance that backpack also. Same thing is going to happen here, which means I'm just going to feel some extra weight. So when the lift is going to move upwards, if you put a weighing scale under me, if you just look at that reading, you will see like extra weight on the reading scale. So that's what this means. Okay, so n equals mg plus ma. When you factor out m, you will have m into g plus a. So that will be the normal reaction. Okay, so when a guy is standing in a lift and lift starts accelerating upwards, lift or whatever it is, okay, when it starts accelerating upwards, you will feel the extra weight. Okay, when a plane is about to take off, all in all those situations, when something is about to accelerate upwards, you will feel that extra weight. So that condition happens when you have acceleration upwards. Okay, so that is this condition, so you will have extra weight. So this is what you need to know, right? So the next case is obviously what will happen when the lift is going to accelerate downwards. Okay, now we will see the second part of the second case. Okay, so here the lift is accelerating downwards, which means the lift is coming from the second floor to the ground floor. Okay, so in that case, the lift was accelerating downwards. You might have felt this one, right? You will feel like slight little bit dizziness when the lift is actually moving downwards. Okay, accelerating downwards. This is because you will feel, obviously in the first situation it was like gaining extra weight, then in this situation it should be like a weight loss condition, right? So whenever you feel like you have lost some weight in that motion, you will get that dizzy feeling. Okay, so that's what is going to happen here. Same thing, you might have encountered this one clearly in aeroplane landing situation, if you had traveled in flight, then you might have experienced this one, right? When the aeroplane is about to land, in that situation you will feel that dizziness, okay? Even when when it is about to take off, that wouldn't be the problem. When it is about to land, in that situation you will feel that dizziness, okay? So that thing, in that situation you might have felt that one clearly, because that their downward acceleration was like greater. But in the lift, if you just sense it and feel it clearly, then you might feel that little bit dizziness, okay? So that is arising because of the weight loss situation. See, if carrying extra weight is not a problem, because we are accustomed to it, right? We will carry load in our hand or in backpack, so we are just used to it. So gaining extra weight is not a problem, because we are just used to it. But the thing is, once you feel like losing weight, so in that situation we will have that dizzy feeling, okay, right? So let's verify it. So if the acceleration was downwards, it should be the weight loss situation. Okay, so let's verify it. So here I'm just going to do the same free body diagram once again. But the thing is, for the someone who is looking from the inside, he will see an extra force that is actually acting upwards. That's going to be the fictitious force that will be acting upwards, right? So now I'm just done with the free body diagram for this particular person. So let's do the equations. Okay, so here you have got summation of force along the y, which should be equal to 0, because he's not going to move along the y-axis from the frame inside the lift. Okay, so summation of force along the y is going to be 0. Now if I just plug in those forces, I'll end up getting the n, okay, normal reaction. So here n was actually acting upward direction, so n, that should be equal to j cap, and then you have got like plus mg, which was acting downwards, so that will be like minus j cap, and then ma, that fictitious force was acting upwards, because the entire lift is moving downwards. Therefore you will have like plus ma j cap, which was acting at upwards, which is equal to 0. Okay, so now if I just do the rearrangement thing, I'll end up getting the answer. Therefore you'll have n, which is equal to negative mg. If it goes to the right hand side, you'll have like plus mg, and then plus ma to the right hand side will give you like minus ma. Okay, so if I just factor out m, you'll have like m of g minus a. So this is pretty obvious. I just lost weight by an amount of ma, because mg minus ma, so this condition is actually a weight loss situation. Okay, so I have lost some weight by a factor of ma. So here, when the lift was accelerating downwards, if you put a weighing scale under that person, you will see like lesser weight when compared to his actual weight, because when it was accelerating downwards, you had fictitious force that was acting upwards inside the frame of reference of that lift. Okay, so you should be clear with the stuff that I've discussed over here. You shouldn't have any doubt. So next we will see the third situation. That will be something different of those two situations that we have already seen. Okay, we'll see what actually it is. The third case is, you have an object or a vehicle that is accelerating towards the right with an acceleration of a. Fine, so this is just the same thing as usual. The difference is, you're just going to place an object in front of this vehicle such that if this object was at rest, this is going to fall down anyway. This is going to fall down, right? But the thing is, once you have some acceleration, some threshold acceleration, which is good enough to squeeze this object to each other, in that situation the friction will be good enough to balance, so that it is not going to fall down. So what should be the acceleration with which this vehicle has to accelerate, so that an object is stuck to its vertically from the front end, it shouldn't fall down? So what should be the acceleration with which it should actually push this object that is in front of it? Okay, that's what I need to find here. Okay, so I think now you are able to understand this condition. So the object that I'm interested over here is this one, that is actually vertically hanging, just sticking to this vehicle. Okay, so I just have to do the free body diagram for this particular object. Then I'll put like summation of f of x, and then I'll also put like summation of f of y. So with that, by combining those two, summation of f of x and then the f of y, I'll be able to get that acceleration. So what should be the acceleration with which it should travel, so that this object is not going to fall? If the acceleration was obviously greater than that one, then the friction will be like good enough to balance that one. Okay, so either it should be equal to that acceleration that I'm going to get, or it could be greater than that one. That is not a problem. If it was less than that acceleration, then obviously this will slowly drag downwards and it will fall down. Okay, so here now I'm just going to put all those vectors into it. So you will have a fictitious force that is acting opposite to the direction of this entire system. So the fictitious force will be towards the left. Okay, so the entire object is moving towards the right, so the fictitious force that is acting on this object will be towards the left. Okay, so that will be like ma. So here one is moving forward, the front one is like with the lesser velocity, therefore those two things will just squeeze each other. Okay, that is responsible for the friction which will keep that object in that particular place. Okay, so here ma is towards the left and the normal reaction should be opposite to to that of the ma. Okay, so you are going to have this normal reaction which is opposite to that of the ma. So here this was the surface. Okay, so normal reaction will always act perpendicular to the surface. Okay, so mg is actually pushing it downwards, is actually making it drop. But the thing is, here because of this squeezing you are going to generate a friction. That friction will balance this mg. Okay, so obviously if mg, because of this mg it should not fall down, then so it should be clear there should be friction that is acting between those two surface which should balance this mg. Okay, so here you are having a frictional force which is like acting upwards. Fine, now I'm done with the free body diagram. So here normal force is along the x direction whereas friction is along the y direction, friction and mg. Okay, right, so now first I'll do the summation of f of x which will be equal to 0. Okay, so summation of f of x, obviously this is not going to move along the x direction for someone who is looking at it from the inside. Okay, so as someone is looking from the inside, we are able to put sum of summation of f of x to 0 and summation of f of y to 0. Same way, because of the guy who is standing inside, I just put like fictitious force. For someone who is looking at from the exterior, in that situation this ma will not come into picture. Okay, right, obviously, because for the one who is standing inside, he will see that there is some extra thing that is happening, that's called as fictitious force, right? So here you have got summation of f of x which is equal to 0. Okay, and then you two have got like n which is acting along the positive I cap, and then plus ma which is acting towards the left, so that's going to be like negative I cap which is equal to 0, right? So here n will be equal to ma. So now I have got the normal reaction that is acting on this particular object, right? So normal reaction isn't necessarily created by the gravitational force at every single situation. In this case, it was created because of the fictitious force. Generally, so at every time, normal force should be perpendicular to the surface. That's why it's called as normal. Okay, right. Summation of f of x is done. Then what we are going to do is summation of f of y. Okay, so summation of f of y, this 2 is obviously 0 because we want this object to be at rest without falling down, right? Or else it will automatically drop down. That should not happen. Therefore, summation of f of force along the y should be like equal to 0, right? What is the component that is along the y direction? You have got like f, that is like j cap, and then you two have got like plus mg, that will be like minus j cap, right? Which will be equal to 0. Now I'll remove those j component and I'll just put in like mu sn instead of fs. Okay, so fs will be f will be like equal to mu sn minus mg, which should be equal to 0, right? So the maximum frictional force that is possible to generate over here should be good enough to balance this mg. If f max wasn't good enough to balance this mg, then obviously this will start dropping, right? So instead of n, I'll substitute like ma. So here normal force depends on the acceleration of that entire system, ma minus mg, which will be equal to 0, right? You should be clear with this one. So here normal reaction actually depends on the acceleration of this entire system. If the acceleration was greater, then in that situation n will be greater, which means friction will also the maximum friction that could be generated will also be higher. Okay, so the friction that is getting generated in this situation depends on the normal reaction. Obviously, that normal reaction depends on the acceleration of that object. So more the acceleration of that entire system, more the friction it is possible to generate, more the f max it is possible to generate. Okay, you should understand this idea. Now let's cancel out the same stuff. You have like m, those two things will get cancelled out. Just do the rearrangement thing, you'll get a. Okay, so the next step will be like a, which will be mu sa, right? So mu sa which will be equal to g. So for a, if I do the rearrangement thing, you will have G divided by mu S. A will be equal to G divided by mu S, right? So it is obvious if the acceleration was equal to G divided by mu S, the F max will be good enough to balance this mg. If the acceleration was greater than that one, then the maximum frictional force that is possible will be greater when compared to this mg. So in that situation, so it will just reduce some, if still more weights could be balanced, but actually those amount, that much amount of friction is not needed. Therefore friction will be less. F max hasn't been reached yet. Even in that case itself, mg was able to be balanced. Okay, so a should either be equal to or greater than that of G divided by mu S. That is when the object will not fall down from that vertical position where it was literally hanging, something like that. Okay, so fine. So that's what I've written over here, the statement for this equation. To prevent object from falling down, acceleration should be, how should the acceleration actually be? It should be either greater than or equal to, right? It should either be greater than, okay, or equal to, what's the thing that I found over here? It's like G divided by mu S, right? G divided by mu S, right? So this is just the statement for the equation that I've generated over here, right? So to prevent the object from falling down, the acceleration should be either equal to or it should be greater than that of the threshold acceleration. That threshold acceleration is actually equal to G divided by mu S. Okay, so I think you are comfortable and clear with this third case that we have discussed over here. Then we are into the last part, which is like the final case. In the final case, we'll do the same thing, but the thing is we are just going to place this object on an inclined slope. Okay, instead of this vertical stuff, I'm just going to place it on an inclined slope, and I'll do free body diagram for this particular object. Then if I do it, we will get to know what should be the acceleration so that it is not going to slide down. That's what we're going to see as the final case, which will be the fourth case. Okay, in the fourth case also you have like two conditions. One is for the smooth surface, and obviously the other one will be like rough surface. In the smooth surface condition, you do not want to consider the friction between the surface of the object and then the inclined plane. Okay, so you shouldn't consider the friction between those two things. Fine, so that will be the first part. So in the first case itself, we will do all those free body diagram with respect to this inclined object, so I'll be able to use it straight away for the rough surface. Okay, so smooth surface is something where we will do those mathematical stuff. Rough surface is something that you will get it straight away. Okay, so here also you have a vehicle, and then the front end is inclined, not the vertical, not the flat one as in the case of the previous stuff. Here it was like at certain inclination, and then it was accelerating towards the right with an acceleration of a. Okay, so this is just the same setup. The only thing is the front part is inclined, and then I'm just going to place an object over here, right? If this object shouldn't slide down, then what should be the acceleration with which it should accelerate, right? Then what could actually happen if the acceleration was greater than this a? That too we will just determine in this case. Fine. So here, what should be the acceleration with which it has to accelerate so that this object which is on the front shouldn't slide down? So what should be the acceleration? That's what I need to get. Okay, so here, as usual, in majority of the situation, okay, only one exception is there. That too we will see in the next theory part. In majority of the rest, all other case, we will take coordinates such a way with respect to that inclined plane. Okay, so with respect to that inclined plane actually means you will take the horizontal to that of, similar to that of that inclined plane, and the vertical axis, y axis, will be vertical to that of the inclined plane. So that is how I'm just going to take it. Fine. So here for this body you have got like mg that is acting downwards. Obviously normal reaction will be perpendicular to that of the surface, right? So these are the things that I've given you straight away. Then we'll have to put all those rest forces that is acting on it. Okay, let's do the free body thing for this object. So here you will have, obviously, fictitious force will be opposite to that of the acceleration of this entire setup. Therefore you will have fictitious force that is acting opposite, which will be like ma. So this thing is done. Then let me do the splitting with respect to x and y coordinates. So I'll be able to split mg into two things, which will be like this component. Okay, so and then you'll have like this component. Obviously I'll have to match theta here in this situation. If I'm just going to match it, so this line is perpendicular to the bottom one and this line is perpendicular to this one. Sure, this should be my theta, right? So this will be my theta. So this will be my theta, then this component, okay? So after splitting, this component will be equal to mg cosine theta. So let me write it this way. So this will be my theta, therefore this component is mg cosine theta, then this component will be like mg sine theta. Fine. So now I'm done with the mg cosine theta and then the sine theta. Okay, so in the previous cases I just drew the diagram in this fashion. Okay, in this case I just drew it the other way around, therefore you got this component to be like mg cosine theta and this will be like mg sine theta. Always the component that is responsible for the sliding will be like mg sine theta, right? Okay, so this one is done, and then I'll have to do the splitting for the MA. Got it? I just have to do the splitting for the MA, right? So this will be like my MA, and then I'll have to split this component into MA cosine theta and then the MA sine theta with respect to x and y coordinates. So if I do the splitting, this will be along the x and this should be along the y. Now I'll have to match this theta, right? So to match this theta, first let me draw this diagram. So let me put it this way. You have like perpendicular one, so this diagram, okay? So this is just a perpendicular 90-degree cut, 90-degree angle. Then I'm just going to draw another one. So I'm just going to move this, tilt this by an offset of some theta. Okay, so if I just do it that fashion, so you're going to generate some theta over here. Okay, so this angle was like theta, then this 90-degree angle would also have moved, the other line would also have moved by the same offset, right? So if this angle was like theta, then this too should have been like theta, right? I think you're able to understand this one. By which factor I have moved this one, the same factor would have been generated on the other side, right? Same theta would have been created on the other side, right? So these two theta should be the same, right? So these are like simple imaginary geometric stuff, right? I'm just going to tilt this angle by certain inclination. So the whatever theta that got generated this on the one side, the same amount of theta would have been generated on the other side, right? So you made the angle theta that swept over here was some angle, same angle would have been swept on the other side, right? So if this was equal to theta, this was like 90-degree, and then you got like other 90-degree, this one, right? These two angles could have been on top of each other. Now I just moved an angle of theta, certain inclination, so same theta would have been generated on the other side. So this angle, so the theta over here is this one, so this will be my new theta. Okay, so this one will be my theta. So these two thetas and these two thetas are just the same thing. Okay, so for this vertical stuff, so something that is close to the theta will be like cosine component, therefore this one is like m a cosine theta, and then this one is like m a sine theta. Okay, so now I have got mg cosine theta, same way I've got like ma sine theta. I've just split everything, so this component is like ma cosine theta and this one is like mg sine theta. Fine. So the normal reaction, if I'm about to do the force balance along the y direction, so normal reaction will be equal to that of ma sine theta plus mg cosine theta. Okay, I'm just not in need of this normal component because friction is not getting involved, right? So only when you have friction getting involved, I just need like this normal reaction. But in this case, as we do not have any friction, I'll just go straight away with the summation of f of x. Okay, so when I put like summation of f of x, obviously I'll be able to equate ma cosine theta with that of the mg sine theta. Okay, so here summation of f of x, summation of f of x, obviously this should be equal to 0 because what should be the acceleration for which this object is going to be at rest. Therefore the object is not moving for someone who is looking at this object from inside the frame of reference. Okay, so here you will have ma cosine theta, that will be like plus I cap, right? So ma cosine theta I cap and then plus mg sine theta minus I cap will be equal to 0, right? Yeah, that's obvious. So if I just do the rearrangement thing and then I cancel it out, I'll end up getting the a. So you'll have like ma cosine theta, which is equal to mg Sine theta, those two m's will get cancelled out. So A cosine theta will be equal to G sine theta. If I just do the rearrangement thing, you'll have like A, which is equal to G sine theta divided by cosine theta. That's going to be like G tangent theta. Okay. So the answer here is A, which is equal to G tangent theta. Right? If the acceleration of this object, if this entire system was equal to G tangent theta, in that situation, this object is not going to slide. It will be in its position without motion, which means at rest. Okay. If the acceleration was lesser than this one, then obviously ma cosine theta will not be sufficient enough to balance this mg sine theta. Therefore, this will start sliding down. That is obvious, right? If a is greater than g tangent theta, in that situation, ma cosine theta will start dominating when compared to mg sine theta. Pretty obvious. Therefore, this will start moving up the inclination with that extra acceleration. Okay, after balancing this ma and then mg with that extra acceleration that is greater than this of g tangent theta, it will start moving, it will start like moving up. Fine. So that's what is going to happen, right? The reason why it starts moving up is because you do not have any friction into it. If you had friction, then obviously that extra frictional force will push it downwards. Okay, right? So that's what is it's going to happen over here, right? You should be clear with that this one. In the previous case where the cut was like flat vertical, in that situation it just got squeezed. Okay, in this situation it is at an inclination, therefore that extra ma component, okay, which is ma cosine theta in this situation, was responsible for the motion of that particular object in an uphill direction. Okay, right? You shouldn't have any doubt in the theory that we have discussed over here. The statement is also the same thing that I've written over here. If the acceleration is g tangent theta in a frictionless inclined surface, the object will be static. When the acceleration is greater than g tangent theta, it moves up and vice versa. If it was less, then it will start sliding down. Okay. I hope you are clear with this stuff that we have discussed over here. So now we are into the last part, which is like rough surface. Fine. Next, with the case of rough surface, we will not be doing more of mathematical stuff. We will see the same free body diagram that we have drawn earlier. Only thing that we are going to put here is in which direction should I put the friction. That's what we are going to see over here. Okay. So here too, you get the same thing again. You are having a vehicle that is traveling right with an acceleration of a, and then you are having inclined surface on the front. You just put an object over there on the inclined surface. Same way, when you do the free body diagram, it will be same as that of the free body diagram that we have already seen. You will have like mg that is acting downwards, right? Then if I split these two components, you'll have like mg sine theta that is responsible for the sliding, and you will have like mg cosine theta that will be responsible for the normal reaction. Okay, these two things, same splitting. Then obviously you will have like fictitious force that is going to act opposite to that of the direction of the acceleration. So ma will be like towards the left. Okay, I just need to split this one with respect to these two coordinates. So you'll have like ma cosine theta towards the x, and then ma sine theta which will act towards the minus j cap. Okay, so these two theta should be same. That is something that we have discussed earlier. These two things are at 90 degrees to each other. Then obviously this theta and this theta are just the same thing, right? So all these things are something that we have already seen. Only thing that I'm going to put extra over here is the direction of the friction. Okay, so if ma cosine theta is dominating, which means acceleration was greater than g tangent theta, in that situation ma cosine theta will obviously be greater, right? So this thing wants to slide upwards, then friction will not allow this motion, therefore friction will actually act downwards. Okay, if in the case g tangent if it was like less than g tangent theta, in the situation it wants to slide downwards. Okay, if a was less than g tangent theta, in that situation it just wants to slide downwards. If that was the case, then friction will act upwards so that it doesn't allow this block to fall from this inclination. Okay, so these are something the straightaway things that we have already seen, right? So that's the statement that I've written over here. In a rough inclined plane, when acceleration is greater than g tangent theta, the friction acts downwards and vice versa. Okay, and other way around is also true, right? So you should be clear with all those concepts that we have discussed in this class. This is, I think, lengthier session. In the first half of the session, we did see the leftover things that are related to friction, where we saw kind of a coefficient of kinetic friction, coefficient of static friction, and the graph. And then we did see mu s, which was equal to g tangent theta, by doing one simple experiment using that inclination. Okay, so to find the coefficient of friction, that is the experiment that we could actually use, right? So then we just jumped into a bigger concept which is called as fictitious force. So fictitious force is something like an imaginary force that has been artificially generated, something like that you will feel in that object. Okay, so that did happen because the entire system was accelerating. Okay, we didn't know that one. When you look at from the inside, it seems to be like an artificial force that has been generated, so that is why it is called as imaginary or fictitious forces. Okay, so that fictitious forces will always be opposite to that of the effect that is happening to that entire system. Okay, and then we did see like 4 different cases related to that fictitious forces. You should be clear with all those 4 cases. Okay, so from this 4 cases you will be able to solve all those different kind of sum. Only thing is you should know how to input this idea into those sums. That's what you need to know, right? So you shouldn't have any doubt in the theory that we have discussed in this class. It should be clear. With this, the video gets completed. Bye.